In lecture 3, welcome back after lecture 2. In this lecture, we will discuss about the De Morgan's laws and especially about the circuits in series form and in parallel forms by logic gates, in which logic gates and or not will be used. So we will discuss in this lecture, discuss the previous lecture summary, which was discussed in second lecture. Logical equivalences, we discussed De Morgan's laws and tautologies, contradictions, laws of logic, logical equivalence using logical laws. Now in this lecture, this is the outline of this lecture: conditional propositions, negation, inverse and converse of the conditional statements, which maybe we discussed in the last previous lecture. Contrapositive, biconditional statements, necessary and sufficient conditions, conditional statements and their equivalences. Most of the topics were also discussed in the previous slide, so we can review in this lecture. Conditional propositions, we already discussed. If P and Q are propositions, the conditional of Q by P is if P then Q, or P implies Q, P implies Q, P implies Q and is denoted by P implies Q is false when P is true and Q is false, otherwise it's true. We already discussed, if you work hard then you will succeed. Implications, if then, we also discussed this. This symbol is used, arrow. This is the truth table for implication. P, Q, these are the values of P and these are the values of Q. P implies Q have the values this. Now interpolating conditional statements, which we have discussed in the previous lecture also. The online user is sent a notification of a link error if the network link is down. The statement is equivalent to, if the network link is down, the online user is sent a notification of a link error. The statement becomes Q if P. P implies Q. And the second examples, when you study the theory, you understand the material. We briefly described this in the previous slides. If P is you study the theory, then Q means you understand the materials. So P implies Q. Studying the theory is sufficient for solving the exercise. So if you study the theory, you can solve the exercise. So the statement becomes, so P is sufficient for Q, so P implies Q. So other forms of conditionals, if P and Q are statements, then P only if Q means if P then Q. It may be John will break the world's record for the mile run only if he runs the mile in under 4 minutes, is equivalent to, if John breaks the world's record, then he will have to run the mile under 4 miles. So if P then Q. This is the activity which shows that P implies Q equivalent to negation of P or Q. This shows that a conditional proposition is simple, a proposition form that uses a not and an or. We show that negation of P implies Q implies P and negation Q. This means that negation of if P then Q equivalent to P and not Q. This is the solution of this. If these are the values of P and these are the values of Q, I already mark all these values. P implies Q having these values. Negation of P or Q. Negation of P, we this table, negation of P is this, negation of Q is this, negation of P or Q. Negation of P implies Q. Negation on this table, on this column, and P implies negation Q. From the above table, it is obvious that the conditional proposition is equivalent to not or proposition. Its negation is not of the form if then. Negations of some conditionals. If my car is a repair shop, then I can't get the class. I already discussed this example. My car is the repair shop and I can get the class. So you can easily solve these negations. Now we discuss about the converse and inverse of the conditional. Suppose the conditional proposition of the form if P then Q is given. The converse is if P then Q. The inverse is negation P then negation Q. Symbolically we represent these in this form. The converse is not equivalent to the given conditional, and similarly the inverse is also not equivalent to conditional propositions. We already discussed in previous slides. If an object is a triangle, then it is a polygon. It's true. But the inverse, if an object is polygon, then it's not. If the object is triangle, then it's not a polygon. Contraposition. The contrapositive of a conditional proposition of the form if P then Q is if P negation then negation Q. Symbolically the contrapositive of P implies Q is negation Q implies negation P. Conditional proposition is logically equivalent to its contrapositive. I solve this in as a rough. For example, today is Sunday, then tomorrow is Monday. We discussed the biconditional if and only if, which we have already discussed in the previous lecture. This is the truth table for biconditional. So here is the interpreting necessary and sufficient conditions. We discussed this example. If a number is divisible by 10, then it is divisible by 2. So I found the summary of the previous lecture in these examples. If John is eligible to vote, then he is at least 18 years old. This was also discussed. John is eligible to vote is sufficient to ensure that he is 18 years old. Here is if John is at least 18 years old, then John is eligible to vote. This will be true. So this is the necessary sufficient conditions. If we denote R and S are two propositions, R is a sufficient condition for S means if R then S. R is necessary condition for S means not R not S. So R is necessary and sufficient conditions for S means R if and only S. So these are the logical equivalence of conditions propositions. We prove this. We already proved in the previous lecture also. In this I'm trying to prove this. First of all, we use De Morgan's law, and the second in conditional rewritten as disjunction, double conjunction negation law, and in this De Morgan's law, again De Morgan's law and double negation. In this we use distributive law, and associative law is used in this step. Idempotent law is used in this step. Distributive law also used, and in the last one we used computative law, and it is equivalent to right hand side. Conversion of statements into symbols. Write these system specific specifications in symbols using the propositions. The user enter the user enters a valid password. It's B. A. Access is granted to the user. C. The user has contacted the network administrator. And logical convectives then determine if the system specifications are consistent. The user has contacted the network administrator but does not enter a valid password. So C and negation V. C. The user has contacted the network administrator and the user enters an invalid password. Negation of V. You can understand about this. This is V. If the negation of this means the user enters an invalid password. Access is granted whenever the user has contacted the network administrator or enters a valid password. It means C or V implies A. This is C and this is A implies C or V implies A. Access is denied if the user has not entered a valid password or has not contacted the network administrator. Negation V, or this V is for using for or. Negation C implies negation. Now we translate the system specification into symbols. Whenever the file is locked or the system is in executive clearance mode, the user cannot make changes in the data. Let me take the file is locked. L represents the file is locked. E, the system is in executive clearance mode. U, the user can make changes in the data. L, E and U. Then the statement is symbolically formed would be L or E, the file is locked or the system is in executive clearance. If the user cannot make change in the data. Whenever the file is locked or the system is in executive clearance, the user cannot make the changes in the data. This statement is written in this form. I hope so you can understand easily. Now the previous lecture summary here we discussed. I am trying to justify with step-by-step lecture summary so that you can easily understand these conditional propositions, negation, inverse and converse of the conditional statements, contrapositive, biconditional statements, necessary, insufficient conditions, conditional statements and their logical equivalences, translating English to symbols, which we discussed in the previous slide. This was a summary in this. We will discuss about the applications of logic. In this, we will discuss about the basic logic gates, circuits using logic gates, Boolean algebra, adders, reductions of circuits. Basic logic gates. Not, where x bar means negation of x, and where xy is x and y, or where x plus y, x or y is equal to NA, N, A and D, where negation of xy is equal to xy bar. This is the representation. NOR XOR. This is for the basic logic gates. X implies x bar, where x negation x, and for AND xy is equivalent to x and y. Symbolically, basically we use this, and in this xy, x plus y, xy negation. For NOR, xy implies x plus y bar, and for XOR, xy x. If we discuss about switches in series, here is the circuit. Here is the point P and is Q. This is the light bulb. For open we use this, and for closed we use this. Now these P and Q are open. So if P open, which is P closed and Q closed, then the status of the light bulb will be on. And if one is open, that is P closed, Q open, then it means light bulb off. If P open, Q closed, then the light bulb is off. And if both are open, then the light bulb status is off. Now we discuss it in switches in parallel. Here is P and Q are shown in parallel. This is the light bulb, and now we discuss it in tabular form. P closed, Q closed, then the status of the light bulb on. When P closed, Q open, then it's on. If P open and Q closed, then it's on. If both are open, then the light bulb is on. Switches in series, if we discuss it in table form, closed, true, closed, true. This is similar to this. We can say this is equivalent in this form. And P and Q, when now we discuss switches in parallel. If in tabular form series, switches P closed, Q closed, then status on, closed, open, then the light bulb on, and open, closed, the light bulb on. If P open, Q open, if both are open, then the light would be on. If we equivalent it to the into the form PQ OR, in parallel we can say this in OR. If P true, Q true, then it's true. P true, Q false, then it's true. And if both are false, then it's false. Now we discuss about NOT gate. A NOT gate or inverter is a circuit with one input and one output signal. If the input signal is 1, the output signal is 0. Conversely, if the input signal is 0, then the output signal is 1. Here if P is 1, then R is 0. If P 0, R is 1, which shows in this table. Now AND gate. In AND gate, an AND gate is a circuit with two signal with two input signals and one output signal. If both input signals are 1, the output signal is 1. Otherwise, the output signal is 0. Symbolic representation is here represented in this. This is P, this Q, AND gate. So it represents the results goes to R. If P, Q both are 1, then R will be 1. If one is 0, one of them is 0, then it's 0. If both 0, then it's 0. OR gate. An OR gate is also a circuit with two input signals and one output signal. If both input signals symbolic are 0, then the output signal is 0. The output, otherwise the output signal is 1. The symbolic representation is presented in this figure. This is R, P, this is Q, OR gate. OR gate means if one of P or Q is 1, then if P1, Q1, then output R is 1. If P1, Q0, then it's 1. It means it's OR, P or Q. You can see as a union. If both are 0, then it's 0. Combinational circuit. The combinational circuit of and NOT are presented in this diagram. P, Q and R. It goes to OR. Now we determine the output for a given input. Indicate that in the below circuit, when the input signals are P is equal to 1, Q is equal to 0 and R is equal to 0. P1, Q0, R0. Then we determine the following circuit. If P is 1, now we solve this. P is 1, Q0, R0. P1, Q0. In AND gate, it should be 0 because both should, if we want here 1 in AND gate, then both should be 1. And if here is 0 and is not gate, so here is the 1 signal. And if this is 0 signal, then 1 and this 0. In OR gate, it should be 1. This will become 0 if both are zeros. This and this one will be 0. Now we labeling this intermediate outputs. These intermediate outputs X and Y. Now we find a Boolean expression for a circuit. Here is P and Q, R, and this is with OR gate, and this P is directly with R and OR gate, and it both combined with AND gate. Now we find the solution of this. This P, Q and R are now this solution is P or Q and this solution is P or R because this is interlinked with P and R. So OR gate, so P or R. Now with we combine it with AND gate, so P or Q and P or R. Here P or Q and P or R is the Boolean expression for this circuit. Now the circuit corresponding to a Boolean expression, it's an exercise for us to construct the circuit for the Boolean expression P and Q or negation R. This is P, Q, this is with AND gate and it's NOT gate. This is R, so this is negation R. it's P and Q, and now this with OR gate. So this is P and Q negation R. So we make it in the circuit, which is so much easy to express in this way. Now it's circuit for input and output table. These are the inputs P, Q, R, and this is output S. If P, Q, R are 1, then S will be 0. If P, Q, 1 are 0, S is 1. Now here is the solution for this table. P, Q, R, and this is S. Now here we note that if P, Q are 1 and R is 0, it means P and Q and negation R. And in this row, if P0, Q1, R1, then output S is equal to 0. It means it's negation P and Q and R. So this is the circuit diagram here. P, P, Q, R. This is P, not Q with not and R, and or. Now this the solution negation P. If where is P, negation P and Q and R, and this is with OR gate, so this is the solution S. Next is also an exercise. This is an exercise P, Q, and P is also with AND gate, and here is AND gate, not, and this is OR. Now we find the solution of this diagram. We note that this P is with these AND gates, and this is Q. So this is the solution of P and Q because it goes from AND gate. And if we discuss about this is NOT gate first. So it's negation P and Q. Here is P. So first of all we say negation P and Q, and if we discuss about this is P directly and negation Q because this is Q, and after the NOT it will becomes negation Q, and at the end these all are in OR gate. So we combine these three, P or Q, P and Q, negation P and Q, P and negation Q. These are, it becomes P and Q, or negation P and Q, or P and negation Q. That's why. Here is the constructing circuits. Here is the circuit of the statement. P and Q are negation P and Q, or P and negation Q. We construct the circuit in this. Here is P and here is Q. You can see this is not, this is not, this is and this one is OR. When the current flows in this P and Q, then the circuit will becomes completed. This is the following is the circuit output of the following statement: X plus Y and negation Y. This is X and this Y, and this is AND gate. and this is NOT gate. So after this NOT gate, the Y becomes negation Y, and this X plus Y, when these both will pass through this AND gate, this will becomes X plus Y and negation Y. We can put these X plus Y into a bracket. So this is the circuit statement. Now designing a circuit for a given input output. We design a circuit for input or given output. Here is the output. Inputs P, Q, R, S is the output. If P 1 1 1 1 1 0 0 0, where we previously used true 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 and then false false. Q is true false true true false false. Here we use for circuits 1 0 1 0. Okay, and for R 1 0 1 0 1 0. S is the output, which we can write it as following. These are the inputs P and Q and negation R. P and Q and negation R. You can easily see that these two colored lines showing that P and Q and negation. Here is the circuit of previous input output. Designing a circuit for given output, we describe this diagram. There is the P with AND gates, and this is Q with AND gate, and here is R with NOT gate. After NOT gate, this will becomes negation R. We write here negation R, and this P after this NOT gate, it becomes negation P, and this Q with AND gates and this with R. So after this AND gate, the result will becomes negation P and Q and R, and similarly we can write here P and Q and negation R. So these two expressions, when we combine them with OR gate, so this will becomes negation P. We can write P and Q and negation R. Or this one, the same this expression, negation P and Q and R. So this is the result of this circuit diagram. I hope so you can understand this easily. After we have to focus on this After NOT gate, this becomes negation R, and P after NOT gate, it becomes negation P. And when we combine them in AND gates, this both these both values, when we put in OR gate, we combined these two expressions. Now we will discuss about the Boolean algebra, which is very important in the discrete mathematics. Just like Boolean logic, variables can only be 1 or 0 instead of true or false. Not negation of 0 means it's equal to 1, negation of 1 equal to 0. OR is used as a plus, AND is used as a multiplication. Mean to say, in sets we use intersection and union. Here we use OR for addition, and AND is used for multiplication. So 0 or 0, 0 plus 0, it's 0, 0 plus 1, 1, 1 plus 0. Previously we write true and false for this 0 and 1. 1 means true, 0 means false. So 1 plus 0 is equal to 1, 1 plus 1 is equal to what becomes? It's for u, and 0 multiplied by 0, 0, 0 multiplied by 1 is 0, 1 multiplied by 0 is also 0. So half adder. Now consider adding two 1-bit binary numbers x and y. 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 equal to 10. 10 means 1 0, not 10. It means 2 times, because we are using binary numbers. If we use these columns x and y, 0 0, so carry 0, sum 0, 0 1, so carry 0 and the sum is 1, 1 0, carry 0, so sum is 1. Now 1 1, so carry 1, so in sum it's 0. Carry is x and y, carry x or y. The circuit to compute, that is called a half adder. Circuit of half adder, the sum x or y, sum carry x and y. So you can see this table 0 0 1 1 0 1 0 1, so carry 0 and sum is 0. So here is the sum 1, and if carry 0, sum is 1, carry 1, sum 0. So this is the diagram which shows the above table. Now using half adders, we can then use a half adder to compute the sum of two Boolean numbers, 1 1 0 0, 1 1 1 0. We use these, we add these two zeros, so this will become 0, carry 0, and now this 0 1 is 1, so carry 0. Now this one 1 1, so 0, carry 1. Now these three ones carry what's Now we discuss how to fix that. We need to create an adder that can take carry bit as an additional input. Inputs like X, Y, which carry in outputs, some carry out. This is called a full adder. We'll add X and Y. With the half adder, we'll add 1. The half adder boxes are half adders. Here we highlighted them. Following is the circuit representation of the statement. We already explained these circuits. Now in this slide we express another logical circuit. Here is P and here is Q. We previously, in the previous slides, we express it in different way. P connects with AND gate, and P also connects with this AND gate, and Q connects with this AND gate. Q connects with this AND gate and also with this AND gate, and the third one with this NOT gate. So here is negation Q. Understand? And if we discuss about this, if P connects with this, so here is negation P. And this one is for Q. So we remember about these when NOT gate is between these and P. So after NOT gate, the P will becomes negation P. Now if P adds with AND gate, then it becomes P and Q, and this one, and in this P, negation P and negation and Q, negation P and Q, and in the third gate this P will comes through this gate, and Q. After this NOT gate, Q will becomes negation Q. So it's P and negation Q. So when we combine these in OR gates, so it becomes P and Q, the first term, this one, P and Q, or negation P and Q, or P and negation Q. So this is the expression of this circuit. I hope so you can understand it easily. I repeat this circuit because this is much complicated. If P connects with this AND gate, and this will also connect with this NOT gate. After this NOT gate, it becomes negation P, and this Q connects with this AND gate and this with NOT gate, and after this NOT gate it becomes negation Q, and this AND gate, this result will become P and negation Q, and here we get negation P because this is the negation P, and this line for Q, so it's negation P and Q, and this for P and Q, and now these three combined with this OR gate. So when we combine these in OR gates, so P and Q, or negation P and Q, or P and negation Q. So this is the expression of this circuit. Now we equate these two expressions, P and Q, and negation P and Q, and P and negation Q is equivalent to P and Q. So we use distributive law on the left hand side, then this will becomes P and negation P and Q and P and negation Q. We use distributive law on this one. After this we use the negation law, that is P and negation P, it becomes a tautology T, and Q and P and negation Q, it will become same. Now it's the identity law that the tautology in and Q becomes Q and P and negation Q. Now again we use distributive law on this expression. This will become Q and P and Q and negation Q. Q and P, and then this Q will this. So this is our distributive law we already discussed. Now we use identity law on this expression. It will becomes a tautology T. We discussed in the previous slides. So it's Q and P and T. Now by using the above identity law which we used here, so we used this one in this statement also, Q and P and T, so it becomes Q and P, which is equivalent to P and Q. Do you know about this? This is the commutative law, which one is used in this last expression. So it becomes P and Q. So this is the statement which accordingly which we make equivalent to the right hand side P and Q. So we have to make any two statements equivalent to another by using these laws, and we have to give logic reasons. We have to give any reason to operate any law on this one. If we conclude this lecture into, we conclude this topic in this lecture. So here is the lecture summary. We discussed in the previous slide basic logic gates by using circuits, and we clarify all the circuits, and we also discussed circuits corresponding to logical expressions and reductions of circuits. And in the next lecture we will discuss about the set theory and we will discuss about tabular form, set builder form, and the sets of numbers, system of the numbers, and we will discuss about the Venn diagram, which is too much important in the applications of discrete mathematics. So wait for the next lecture and we will discuss about all these things, especially Venn diagrams, and we will also discuss about the set identities by Venn diagrams, which is clearly useful in the applications of discrete mathematics.